Alright, time for another DraftPhysics.com video presentation. Debate physics also, but again, debate just isn't happening in the proper sequence. Statement, counter statement, that kind of thing. You can't get people to actually respond to the actual argument. So I've made actual arguments repeatedly. I've pleaded that those 5-minute beginnings of videos, that kind of thing, that the actual segments be accurately paraphrased and are played, preferably, and you actually point out how anything stated is you can prove to be incorrect with anything called evidence. And they just won't do it. So this Leksa guy, at least he's making videos, okay, so that's good. He's claiming, it's right in the response to Gary. Well, it's my channel name is DraftScience. It's really not that complicated. Newton, springs, and momentum. This is not really a response to. He's just making his argument again in some other way, with no citation to any experiments or any assertions by a physicist. So, it's not really a response to what I've been saying. So I'm going to begin this video again with a simple statement about the truth, about the actual facts. And you're supposed to refute those facts and point out how what I'm saying is not correct, not absolutely 100% correct. Now, this whole thing, this whole argument between just this simple understanding, mv versus 1/2, okay, and the 1/2 wasn't there in the beginning, so just pretend it's not there. mv squared. This was called the living force, this component. And it was invented by a guy called Leibniz. And he published it about a year before Newton published the Principia, which sort of was an insanely both quantitative and qualitative description of the mechanics of the universe. Including the gravitational constant and lots of other details. And so this idea was just a suggestion, okay, you could argue, as an assertion, okay, and you could call it Leibnizian even, okay. This is Galileo, Descartes, and Newton, who were all very successful physicists getting successful answers. Leibniz was, yes, a physicist. I mean, he was a lot of things, a lawyer, a diplomat, lots of things. There was a, ensuing debate. But I'm just saying there's no point. You're just a Leibnizian if you're defending this. And again, it was called the living force, and it was pretty much invented not because physics demanded it, not because there was some experiment Leibniz could show that clearly illustrated the existence, that there was, that it took 8 times more fuel to go twice as fast. I mean, frankly, without the half, you got really wrong answers. Okay. And my key argument would be is the reason why Leibniz was able to believe it was because it still wasn't quite clear what was causing gravity. Okay. And so clearly Newton pointed out it is 9.8 meters on the surface of Earth, okay, per 1 second. Okay, so in 1 second, you get this quantity. And yes, we have the phenomenon that Galileo illustrated, that you have this 1:3:5 ratio of distance you end up going as you acquire more and more of this acceleration. But the acceleration is the force. The thing that changes your momentum is the force. Those are key statements. The thing that changes your momentum is the force. This changes your momentum. Alright, and so there's this simple argument that this is just an illusion. Okay, you travel 4 times the distance. Alright, so just 1 unit of distance. Okay, 4 units of distance. But what's really happening in the gravity is per 1 second. So it's only time that really matters here. This is in fact 1 unit of time, and this will be in fact just 2 units of time. So you can fall 4 times the distance in only 2 units of time. And clearly the argument can be made that the only place you can acquire this 9.8 is in 1 full second. You have to be in the gravity free falling 1 full second before you get this 9.8. And the simple truth is, the stuff Newton pointed out that Leibniz didn't, is that this velocity, okay, will be exactly 1/2 of this velocity, indicating clearly that this 2 is really important. You'll be going twice the velocity, okay, when you hit the ground here, not 4 times the velocity, 4 units of distance, only 2 units of velocity. So this whole section here, you only got 9.8. This section here, you got 9.8. Those are your 2 units of force. The units of force or acceleration are the only thing changing your momentum. The only thing changing who you are, what you are. And there's clearly only 19.6 when you hit the ground, clearly indicating that you only gained another 1 unit. So something traveling in space, as I've pointed out, an asteroid coming towards Earth could be at 30 miles of distance from the Earth, and it can be traveling at very high speed, and it could travel those 30 miles in 1 second. And all it's going to do is change its speed. Say its speed was 20,000 miles an hour. It's just going to make it 20,009. It's in a 0.8. It's not going to make a substantial difference in its speed. It traveled all that distance through gravity, and it gained nothing because it went through it so fast. And those are the simple facts and truth. Okay, twice the velocity, twice the time. It's only going to be twice the weight. These are experimental facts. This lands, it only hits with twice the weight on a scale, twice the impression on a spring. That's all it's going to do is twice impress the spring. It's not going to 4 times hit the spring. So, this is my argument, that there was no good reason to invent this. This Newton physics wasn't broken in any way. Galileo, Descartes weren't broken theories, and Newton made them even less breakable. And there's really nothing to support this. And there hasn't been for 350 years. Again, you'll show no experiment where it takes 4 times the fuel to go twice as fast. How much fuel it takes really depends on how fast you do things. So if you don't do them at the right speed, you can waste all the energy you want. I can compress this scale very slowly, but the whole time I'm doing it, I'm doing work. So I could take all day to press the scale down. And all day long I'll be doing work against the scale. Or I could just press it and have the lock it, and that's it. I can go the fastest economical speed. That is, I can apply the amount of force that gets it to the location, and then the force runs out. And that's the same thing you can do in gravity. You shoot for a higher location, you can get there much faster, you'll save a ton of fuel, because you'll maximize how you applied the force against the counter force. And those are the facts. Alright, and the rest is going to be just arguments about, assertions and things that have, for which he's not going to show any evidence. I'll play some Professor Lewin clips that illustrate, in my opinion, and I've already stated them pretty overtly. The guy says nature can fiddle with kinetic energy, but nature can't finagle momentum. And you're making an argument for a non-conservation of momentum theory, with the catch that somehow magically in the 1800s they decided that somehow kinetic energy, Leibnizian energy, was a scalar, and Newtonian energy is somehow a vector. And it's just made up. There's no way you could see this vector scalar difference when the train is running down the track. The mv that is momentum is somehow now, that's a scalar. That's going in a direction. All of a sudden it's not going in a direction when I put a square on it and a half in front of it. Now all of a sudden it's not a direction. I mean, I'm sorry, but this is nonsense logic. It just has no logic. And I want you to defend, why the 4D means anything when you'd have to almost be retarded to think that something moving into, say, a range of 30 miles from the Earth, going a very fast speed, where say it takes a second for it to get from where it is to the Earth, that it gains any significant momentum from Earth's gravity, because it's only one unit of time. And the same could be argued about just this simple argument. I have a gravitational body, I fly by it. The quicker I fly by it, the less I get bent. The slower I fly by it, the more I get bent. Why? Because it's a time-dependent force that has absolutely nothing to do with distance. Alright, that's the argument I want you to counter among the other arguments I have made. But I wish you'd stick first to one subject and, in some way prove your counter argument, if you're going to make a counter argument. If you're like I said, you're a Leibnizian. Defend Leibnizian physics. Don't sit there and tell me that, Newton was right. Well, I already know Newton was right. You have to defend how that's consistent with saying Leibniz was right, because I'm saying he wasn't right. He made a kind of a goofy error. Alright, so leave us play the video that I'm claiming is quite unresponsive.
Gary, and thank you for your...
I think we need a little more volume.
Video response. This will be my response to your video.
Yes, I played your video and responded to what you said. You're not playing my video and responding to what I said.
Let's start again with what Newton was actually saying, because I think I realized something quite interesting.
Yeah, well, it's interesting to you. To me, it was already a dead subject. Despard saw the quote. The quote's been done. It's clear what Newton was saying. It's clear he wasn't saying anything about kinetic energy. It's clear he didn't believe in it. Now, I could go research and find the arguments made on Newton's behalf against Leibniz, pointing out how Leibniz is a free energy formula and it doesn't make any sense. And clearly Newton opposed it. So there's this whole F equals ma crap that they derive into 1/2 mv squared, implying that Newton in any way endorsed this theory, is just part of the propaganda. And you should just admit that your science education wasn't in error. It was a quite overt perversion of the truth to imply that Newton had anything to do with 1/2 mv squared.
When I was reading his second law and also some other parts of Principia, so based on this text here and maybe some other parts, I think the safest assumption is that the alteration of motion here means the change in momentum. Not the rate of change in momentum, but the total change.
So I don't even know why this is a subject, the rate of change of... It doesn't matter. It's a change, period. Now, yes, it matters if the whole experiment is 30 seconds and you were changing through the whole 29.9 seconds. Obviously, that's going to have an effect because the change is incremental and it never really, it's taking forever. And so you have to do the average over that entire long period, blah, 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 blah. But that's as trivial as the fact that you only, even when you have the 9.8 meters per second velocity, you've only traveled, 4.9 meters. So your average, based on how far you traveled, is much lower than 9.8. But the fact is, you have a velocity of 9.8 when you finish that voyage. I mean, but that's trivial physics.
Change in momentum. Whereas the conventional definition is about the rate of change in momentum. So
again, I'm saying both of any attention to any rate crap in this conversation doesn't mean much. There's a rate of acceleration and deceleration as things contact each other, and those have to match, as the Newton's cradle proves. But the force is an amount of change. It's just an amount of it.
There is a difference. You have been correct about Newton. I was incorrect in my previous video. So the difference in these definitions is how they relate to time. The Newton's definition describes a change in the system over some period of time.
I'm just saying Newton was clearly focused on gravity, and clearly he's made this explicit point that you get this quantity of change in 1 second. It's a quantity of change. It's a real velocity, 9.8 meters. It's a real thing, and that's what you get per second. You don't get twice that. You don't get 4 times that. You don't get half that. You don't get anything. No, this is what you get per 1 second. As I've stated, if you want to make this a half second, then you can change this number to 4.9. If you want to make it 2 seconds, you can change the number to 19.6. This is the ratio. This is what you get. And it's clear there's only 2 seconds in this 4 times the distance. So again, it's over. The whole subject is over. There's no place for this squared term. There's no place for any of this garbage about how it has more energy, because it only collected 2 units of force. 2 units of force are not 4 units of energy. Of course, Newton would oppose any idea that 2 units of force equal 4 units of quantity of motion, their term for energy.
Whereas the conventional definition describes the system at some point in time. Here we can use a bucket analogy. So
I think the clear distinction between the 2 theories, Galileo and Newton, let's just say, is time versus distance. Okay, Newton's theory, distance doesn't mean anything. Galileo, distance doesn't mean anything. The thing that matters is the amount of time. That'll change the velocity, that'll change the weight.
Buckets collecting rainwater. Conventional definition would be about how fast the bucket is filling up at some point in time.
I don't know why the 2 are drawn exactly the same, because they're completely different answers. I don't know what you're doing exactly at all. Kinetic energy theory says I'm collecting 4 times the energy while I collect 2 units of force. Show that.
Or how heavy is the rain at some point in time. And often that is described as volume per time. And you can make this time as short as you want.
Again, this whole argument about volume is an argument about what you should multiply times each other. Okay, MV, it's a volume, it's multiplied times each other. You're saying that there's some reason to multiply the distance times something, or to do something like velocity times time, when velocity is already a time. The ratio of a velocity is already got time in it.
So basically you can talk about a point in time. And Newton's definition would be how much water was collected during some time, so that would be just volume. So the difference is how these definitions relate to time, and
I don't see the definitions. I don't see anything in here that makes any sense to me at all. I can't see what that. Well, you're not comparing 2 things that are different. You say there's 4 volumes of energy collected in the same time, as Newton would say there was only 2 volumes collected.
Newton's force is what conventional force accumulates into over some period of time.
No, it isn't. So again, I'm sorry. I don't know what you did. It's not the same. They're not the same theories. They're completely different answers to the simple question. In every single case where you're interacting between 2 non-equal masses, these 2 formulas don't give the same answer.
Okay. I have to admit that
don't conserve anything, and conservation is one of the fundamental things here. Galileo, Newton, Descartes all believed in conservation.
I was quite surprised when I realized this, and I think this is quite disturbing from the point of view of science education and history of science. But
yes, I think it's disturbing that these two formulas aren't written on a board and these physicists are actually obligated to explain how I turned this into some kind of new thing by throwing a half and a square on it. I haven't thrown a real thing anywhere. I haven't added anything real. And yet now I've changed this from something that has a direction into something that doesn't have a direction. I mean, it's all mush.
unfortunately, I don't think that this solves any of our problems, because it's just about definitions, about name tags that
whatever this is not a semantics argument. This isn't any of that crap. All right, you're making direct assertions about what happens in the physical universe, and you have zero evidence for it. That's the real subject. Is you've had 350 years to produce a single experiment showing it taking 4 times the fuel to go twice as fast, and you don't have it.
we want to get to different things. So let's talk about the arguments itself, or arguments themselves. So
these aren't arguments. These are just assertions. I'll argue. So, very interesting. You have your own assertions you wish to make that I would argue might not even be Leibnizian. Okay, so, but fine. You have to bake them up with some logic or some physical experimental evidence. I don't see any experimental evidence demonstrating what you say to be true.
in your response video, you were talking about springs and momentums and how I can't explain why springs wouldn't conserve momentum.
Yes, you're not going to show how it doesn't happen. You're not going to in any way say anything to demonstrate how springs don't conserve momentum. You're just going to assert it.
Or how springs would tell any difference between equal momentums.
How springs would tell any difference between, and the whole point is that they have a pressure. If I put a lighter object, I put a lighter cork in my cork gun can only produce so much air pressure. The air pressure will shoot the cork. The lighter cork's going to go half as light cork will go twice as far. That's the simple argument. It's the momentum has to be conserved. Lewin says that. Again, conventional physics believes that, so argue with them. Why are you claiming that I'm making a bold anti-conventional physics theory when they're the ones saying you have to conserve the momentum? I'm not the only one saying that.
So here's a thought experiment about that.
It'd be better to have real experiments to make your point. I mean, a thought experiment is fine if it does something interesting and new that you can't do in regular space. You can do in regular space. This isn't a classic thought experiment. Thought experiments just mean I can't do the real experiment. You don't use thought experiments for experiments you can do.
At least according to my understanding, your claim has been that equal momentums cause equal spring compressions.
I mean, I'm just going to say the word duh. Yeah. That is, I could always find some other thing. I can put a 5 mass going 10 in, and I get a spring compression. Now we know that spring compression produces a 5 going 10 out, if we have a really good conservative spring. And the simple truth is now I can just say, well, what if I put a 10? What if I put a 20? By your kinetic energy theory, okay, that if I'm going to conserve the kinetic energy, I'm going to be able to put a 20 on there and get it to go 5. So I put a 5 going 10 in, and I can get a 20 going 5 out, because that's the same kinetic energy. And then I could take a 40 or a 70, and I'll get more and more bizarre numbers in the sense that they will keep going really fast. And we already have the experiment in the sense that we already have the gun and the bullet. I mean, we already have the extreme experiment, and you have the ludicrous, in my opinion, theory, okay, that 2,000 joules is going this way and only 2 joules is going that way. And you have this silly theory, in my opinion, it's silly. If I take 2 guns and put them inside of each other and I fire the same explosion, that somehow the recoil of these 2 guns will be an insanely increased amount. So when I'm shooting the light bullet, the gun recoil is 2. But if I'm shooting against a gun, somehow it's now a huge, gigantic number. You don't have any evidence.
And I would argue that that just can't be true.
Well, fine. It can't be true because you say so. Okay.
That can't happen. If we assume this, then we are going to run into contradictions.
Right. I wouldn't assume it. I directly oppose it. I directly assert that doesn't happen. They're not. Springs don't collect whatever kinetic energy is. They don't collect it and they don't give it back. What they do is conserve momentum. That's their strong suit. Like a lever, they're able to do the conversion. The simple argument is levers can do the conversion, right? I can have something going fast on one side, higher velocity, more distance, and have something heavy do the opposite, go less velocity. And I can convert back and forth all I want. And springs essentially do the same thing. I can compress the spring slowly, or I can compress the spring very quickly. My choice. But the point is the total amount of force will be revealed in a number, an amount the spring compresses. And Hooke's law basically says springs are linear. They collect force in distant related units. So you can measure the distance of the compression and know how much force is in the spring.
Or at least have some very, very difficult things to explain. So let's first note that when we are talking about spring compression, we can talk about either the length of the compression, meaning how many inches or centimeters we are making the spring shorter, or we can talk about the duration of the compression.
I don't see any point in talking about the duration. It doesn't mean anything. Because depending on what mass I put in front of it, of course, the velocities are going to be different. The duration is going to be dictated by the velocity. So what? That'll be compensated for by the math. The mass is the simple argument. Heavy things go slow, little light things go fast, okay? And it really won't have anything to do with how much pressure they can exert, in the sense that their pressure will be just a simple calculation of their mass times their velocity. Those are the only things that are relevant, and you don't need to put a 1/2 and a square on them. Those superfluous, non-real things don't enhance understanding at all. The real things are mass and velocity. The completely artificial, useless, mushy, cruddy stuff is just this 1/2, whatever that is, and a square, for whatever reason, which has nothing to do with reality again, and is only defended because you people say something as silly as 9.8 meters per second per 1 second squared. Per second. There's no per second. That's not science talk.
Meaning how long the spring feels the weight.
So it doesn't matter how long it feels the weight. It just has to reach the number. That's all it has to do. It reaches a place, it stops, and then it goes back. All the energy is in when it stops. All the energy comes back when it releases. And I can put a little clamp on there and stop it from releasing. And I can see exactly how much energy it trapped. And that's all it's doing. It's trapping the energy. It's absorbing the energy, and you can store it in the spring. And then if you want it 10 years from now, I can go back to the spring and I can get my energy back. You're not in any way refuting that as a diagram of how springs work. They're storage devices.
Here we have two identical springs, two objects with different masses and velocities but equal momentums.
Right, so they frankly are going to compress the spring the same amount, and they're going to, I can just inverse them any place I want to. I can compress the spring with them, and then I could switch which spring they're on, and they're both going to get the same force back. The amount of force you get from the spring is completely dependent on how far it's compressed. Hooke's law. We already know that's a proportionality. So there's absolutely no doubt that there's a certain amount of force and a certain amount of compression. Period. And you come in with the same force, you're going to go out with the same force. They both leave with the same force. The same units of force make something half as light go twice as fast. That's what the same force does.
They hit the springs and compress them. And if we assume that the length of the compression is the same, we have to conclude that this faster object does everything faster, it compresses.
Yeah, and it means nothing, okay? I'm just saying it means nothing. The lever proves it doesn't mean anything, okay? The lever is saying this part of the lever is moving twice as fast as this part of the lever. So what? That just means you can equalize acceleration and deceleration. I can take something that accelerates slowly and put it on, close to the fulcrum, and I can take something that needs to accelerate quickly and put it on the end of the fulcrum, and I can just balance those things just like a Newton's cradle would do if it could do, okay, elastic collisions between uneven masses. But it can't do them because it can't do the conversion. It can't convert between if you're just going to bang two things into each other, without a conversion device, the slow deceleration of one isn't going to match the high acceleration something else needs, a lighter thing needs, to take all of the energy. So it can't take all of the energy. And if it's a heavier thing, it can't absorb the energy because it needs to accelerate slow, and this is decelerating way too fast.
Presses the spring faster, releases the spring faster. So it applies the weight for a shorter period of time.
The weight is the end product, okay? So it doesn't apply a weight. It merely has energy in a direction, and the spring keeps absorbing it until it stops moving in the direction. It's clear the object going into the spring is winning the whole time. The spring isn't fighting back in any real way because it's losing the entire time. And it's not until the spring stops compressing that you have equalized the forces, that you have as much force pushing out as you had pushing in, and now you've equalized, you go to zero. And now the spring has all the energy and will push the other way. It's one way. It's a one-way street. You go one way in and you go one way out.
Meaning that this other spring here, for some time, would feel additional weight.
It doesn't feel additional weight because they weigh the same. That's what the lever proves. The lever, absolutely. So I don't care. I won't even accept any disregard of the fact that I have shown a lever, and everybody knows I can put a 5 mass 2 units of distance and a 10 mass here, and they will balance perfectly, indicating that their weight is exactly the same, okay, if I allow for this circumstance where this one moves twice as fast as this one. So as long as I do the conversion, they weigh exactly the same. So that lever essentially proves, okay, that the 5 mass going twice the velocity weighs the same as the 10 mass going half the velocity. That's an established, I don't see how you can't argue with the fact that levers show you this. So don't tell me about the weight. The weight is the final reading on the spring.
So where does that come from? How would you explain that in terms of momentum alone?
I'm saying momentum always works. You're clearly not showing how this isn't. It's absolutely true that this will compress the spring the same amount as this compression, and that these two have the same capacity to affect the universe. The same ability to push atoms in total. Yes, one of them will move atoms quicker, but it's completely irrelevant.
Or conversely, we can assume that the duration of the compression is the same, but then we must conclude that the length of the compression must be longer for the faster object.
It says you. I don't must consider any of this stuff. This is all just mush. Sorry. I mean, you're telling me I have to pay attention to variables other than the mass and the velocity, and I really don't. Okay, and as I pointed out, I can compress this efficiently or inefficiently. I can use more energy or less energy. I can decide to do it, in all kinds of ways. And the fact is that there's an ideal mass to velocity speed, okay, that's the most efficient. It's the most efficient to get to a location in space. If you want to hit the moon, there's a certain amount of velocity you would have that would be the ideal velocity. Now, it's probably not the best example, so we should say the top of the atmosphere, just so we are going through a consistent gravity. There's an optimum amount of velocity you acquire to do that jump. Too much means you went further than you need to go, so you wasted energy. Too little, obviously you didn't get to the thing, so can't be the efficient. You know. And that's the speed ratio, but it doesn't have anything to do with the fact that each one of these objects has a different ideal acceleration and ideal deceleration. And when the two of them are matched, frankly, you can match an acceleration to a deceleration using an instrument like a spring or a lever or hydraulics or some other mechanism where you can do the conversion.
I think that this clearly shows that
I'm sorry, this is, there's something bizarre, in our miscommunication that you can say this clearly shows anything. You aren't even making an assertion here. You're not even showing in this diagram that somehow these two objects don't compress the spring exactly the same amount. Where did you show me that? I don't see it anywhere. And I could do this in gravity, and I could prove the point that, frankly, I dropped the lighter object from 4 times the distance to double its speed. And the fact is I'm going to end up with the same compression. Gravity will tell me so, because the units of force that I'm collecting will be obvious. They'll collect the same units of force. Now, obviously, if I do it in gravity, I have to subtract the mass of the object from the measurement. If I do it horizontally, I'm just saying I can do it with a pendulum horizontally. I swing the pendulum from 4 times the distance, okay, with half the mass. And I'm going to get the same freaking compression in the spring, because I'm going to collect exactly the same amount of force. I have a half the size bucket, but I'm going to leave it in the gravity twice as long. It will be twice as long. I'm going to collect the same amount of water. The same water is going to hit the spring.
Springs can tell the difference between the equal.
You says you. So again, you're just making assertions. You have nothing. Nothing. You have no evidence of this.
Momentums. And especially it shows that you really need something in addition to momentum.
Says you again with nothing. You're showing me absolutely. You're not even drawing that these two things compress the spring a different amount. You're not even showing me that somehow the total compression, the weight that they put on the spring, the weight, and it is a weight. You're not showing me that they weigh differently. You're not showing me the experiment where they weigh differently. So why are you just asserting it? And I'm saying, of course, that's not true. It wasn't true when Newton was alive, and it's not true now.
If you want to explain these things, momentum alone isn't enough.
So it just says you with zero evidence. Okay, I mean, frankly, you really think I'm going to respond to that with anything but, what the hell? You're just going to tell me what the truth is? Ugh.
Just isn't enough. Okay. Here's a similar example dealing with much of the same thing.
Okay, I stopped playing the video when I got here because this is really stupid, frankly. I'm sorry, this is stupid. I can't call it anything because we've been over this. This we have seen. Lewin has done this experiment. So, no sale.
So we have equal balls here with masses of 10. Then we have a small object and a large object. And compressed springs, we will release the springs, let them push these objects into opposite directions. And just for the sake of the argument, let's make 2 assumptions. The first is that both springs create equal amounts of total momentum, and the second one is that each spring creates equal momentums to both directions.
Okay, wrong. So that doesn't happen. Clearly it doesn't happen. So, as soon as this side yields, right, the light object on this spring means this light object is yielding. This 10 can't possibly go the same speed as it's going to go here because it's getting all the energy here because this is not going to yield at all. So yeah, the more a surface yields, the less the thing can bounce. The more I throw a tennis ball at a wall, if the wall starts moving, the tennis ball is not coming back at the same speed. And if it moves really, really easily, the tennis ball is not coming back at all. So, I mean, yeah, no, I don't agree with your assertion, okay, that these two systems apply their momentum and it's the same way. They don't. So you could make the argument that if you could, well, the gun one's a little dangerous just because explosions are different than just gas pressure. It's a little more complicated than that. There's heat involved, and you really can't reflect the heat. So, there's different ways of understanding what's pushing the bullets and the objects. But the idea would be is that you could increase the velocity of the bullet by making sure the gun doesn't recoil. The less recoil, the less you allow it to recoil, that is physically move, the higher the velocity of the bullet.
Based on these assumptions, we can conclude that the 10 mass balls will gain equal velocities.
Well, you concluded. I completely disagree that, especially at these ratios, the 10 mass is going to get a tiny fraction of the energy, and the 1 mass is going to get the substance of it.
So
the momentum. There has to be a limit to how far you can go in terms of the differential between the objects, right? So you can say if they weigh the same, it's simple. If it weighs twice as much, you can get pretty close. You're going with 10-to-1 ratios, and frankly, at 10-to-1 ratios, you're not going to get the same distribution of the momentum.
Obviously, they will gain equal momentums, and since they have equal masses, they will gain equal velocities.
Okay, well, I'm just saying, you don't have any experimental evidence showing that to be true. So there's no way that in these two experiments, this 10 mass is leaving with the same velocity. It's just not going to happen.
And does this make sense to you? Does this seem reasonable?
No. Yeah, that's a simple enough answer. Just imagine that I change this 10 mass to a 1 mass. Well, now we know the energy is going equally in both directions. And the heavier I make the 10 mass, we know the 1 mass is going to go faster. So we know the 10 mass has to go slower. I mean, if I make the mass 100 here, we know the 1 mass is going to leave with twice the speed that it would leave if both sides yielded. I think understanding it as a yield argument, if one side can yield much easier than the other side, then you're automatically taking away energy. You're automatically subtracting energy that can go the other way. If it's yielding, you can't bounce a ball off of it.
These balls here, with identical springs, would gain equal velocities.
All right, so again, let's just understand each other that, okay, it's fine for you to say so. I say this is not illustrated by any routine experiments done in physics, and I'd say the routine experiments done in physics don't say this.
So this ball here is pushing against a tiny object, and this other one is pushing against a large object.
I mean, you take it to an extreme. You're just basically saying, look, I'm going to take a lead cannonball and I'm going to put a spring in, and then I'll put a feather on the other side. Do we have any expectation that the lead ball's going anywhere? Not really.
I don't think that you believe this to be the case. So, at least one of our assumptions must be incorrect.
There you go. At least one. I'm saying it goes back to one thing. I'm just saying you believe in a theory. You're just saying, look, here's momentum, mv. You're saying it's broken somehow. All I'd like you to do is show in some elemental experiment where mv gets a wrong answer. That's all. What's so demanding? Just show me where it gets a wrong answer.
Which one? I would say that assumption number 2 must be correct. I think that springs always create equal momentums to both directions.
Well, they don't. The spring actually does, its center of mass moves in a direction. If the center of mass moves in a direction, it's obviously going to push more stuff in the direction its center of mass is moving. So I guess that would be a way I understand it. If the spring starts expanding unevenly, then the center of mass of the spring is moved. And now the explosion is essentially further away from one of the objects. And so it's not the same distance between the two objects, so it's getting less of the energy. You could just sort of understand it that if the center of the mass of the spring was a sun, and you're saying how many photons are hitting the two surfaces, you could argue that if the sun is moving away from one and closer to the other, that yes, the little one's getting a lot more photons than the big one.
So in that sense they are balanced, meaning that assumption number 1 must be incorrect.
Sorry. There was no evidence of anything. I just don't understand it. You say meaning something must be incorrect when you don't have any confirmation of what actually happens.
So in that sense they are balanced, meaning that assumption number 1 must be incorrect. Identical springs don't always create equal amounts of total momentum.
I don't even know what that means. Identical springs, the same compression has to create the same momentum. So again, and you have no experimental evidence showing otherwise. So until you show me experimental evidence where the same spring compression doesn't create the same total momentum, you don't conserve momentum with a spring. I'm saying no sale. Completely no sale. And the only rule is that you have to be within the spring's tolerances. You can't stack a whole bunch of springs on top of each other and then not use a quick release and all of that stuff. You have to do the experiment correctly.
It depends on the objects that the springs are pushing.
Nonsense. The spring only has so much to give, and if I put two immovable objects on either side, it's not going to move them. And it's not going to move with more, it can't give anything more momentum. The force is actually in the spring. I mean, you're just not getting that part, right? I drop something in gravity, I drop it onto a spring, the spring compresses. The thing that had motion has lost all of its motion. All of its motion is in the compression of the spring. If I lock the spring in that position, I can't make it have anything more than 2 units of force, let's say. It collected 19.6 in velocity. It collected, I can't, it's hard to describe the force units without getting to mass and momentum. But it collected the momentum, the mass times the velocity. That's what it collected as weight. There's a couple of units of force in there, and that's all there are. Defined by the mass. And that's it. The momentum is trapped in the spring, and all you can do is give it back. I put a light thing on the spring, it goes fast. I put a heavy thing on the spring, it goes slow. Completely consistent with momentum. Where do you have experimental evidence that that isn't true?
But again, I think this shows that momentum alone is not enough. You need something else.
Well, it says you, and this I don't see how you showed anything at all. Nothing. I don't see any show here.
Then one more thought experiment. This is basically the same as the gun and the bullet in the previous video. There I was trying to make a point that I thought was quite important.
Yeah, I'm sorry. It's based on, again, no experimental evidence. So you're basically saying the recoil of the guns you can make them go faster somehow. You can change the recoil. You can change the total momentum. I'm saying I don't see how you do that.
But I felt like you didn't quite understand that. So here I try to...
If you conserve momentum in every single experiment that could ever be done, then I'm saying, yes, you've proven MV, and you've disproven MV squared. Now, if you can show me one experiment where you actually do conserve this MV squared stuff, that is starting with momentum, then fine. But you're not going to show me that. I'm saying the disproportion of evidence on one side versus your side. Your side is round objects in clay, and as I pointed out in the beginning of this video, a kind of silly understanding of how gravity works. So besides those two piles of crap, you have nothing on your side. You have nothing indicating it takes 4 times the fuel to go twice as fast. Nothing.
Make it in a more clear fashion. So again, here we have a heavy object, a light object, compressed spring. We will release the spring will push both of these.
So let's understand, it's dramatic difference in the masses, and so yes, there's going to be a dramatic difference in what's going to happen in terms of the distribution of momentum. I'll clearly state that the heavy object isn't going to get any momentum once you get heavy enough. That's the whole point here. You're saying, in a sense, it gets twice the momentum, frankly. Your theory basically says it's going to get twice the momentum because of your, whatever, your scalar stuff. So because this did 2 different motions, in and out, you're going to say there's 2 motions inside of this in one direction.
Objects, and obviously the lighter object will travel further distance within some unit of time. Let's also decompress the spring like this. And again, I would argue that it's quite easy to see that most...
whatever. There's nothing to see, okay? You're not showing any, you're providing 0 references to any well-conducted experimental evidence.
Of the length of the spring was traveling to the direction of the lighter object, and a smaller part of the spring was traveling to the direction of the heavy object.
The fact is, the spring can't travel till it actually pushes one of the objects out of the way. The object has to move before the spring can move in that direction. And you're just basically saying, yes, if one side yields substantially faster than the other side can move, then the spring will release more energy, more of its momentum to the lighter object. Yeah, that's one of the quirks, is that you start moving the center mass of the explosion, essentially.
And based on this, we can conclude that there must be this kind of division line, that on the other side of the line, all the spring was traveling to the direction of the lighter object, and on the other side, all the spring was traveling to the direction of the heavy object.
I think you're saying the same thing here, that obviously there's a center mass, but obviously in this case it'll never go towards the heavier object, so you'll never get more, or whatever.
So basically there's a point in the spring that wasn't moving into any of these directions. Which means that we can basically imagine an immovable wall here. Because nothing was moving here where the wall is. So we can just imagine an immovable wall here. And now we can also see that we basically have 2 springs on both sides of the wall. One long spring and one short spring. And the lighter object, which gains higher kinetic energy.
Higher kinetic energy, again, whatever that is, right? I thought we were talking about momentum and conservation of momentum. I'm saying you're going to conserve the momentum, so it's really a moot point. You can't make the kinetic energy because it's more momentum than you started with. You can't do that.
Was pushed by the longer spring. Makes sense, right? And again, if we rewind this scenario, so we make the objects approach each other, and
I'm saying you have a spring compression. It just doesn't matter what you do with the masses. If you just push one mass off of the Earth, or you push 2 masses apart, you have to conserve the momentum, the force that's in the spring. Whatever the momentum is that compresses the spring that much, you have to produce that much momentum out. And how you apportion it will just be based on how differential the masses are. The more differential they are, then the more you're going to be one-sided in who gets the bulk of the energy, the momentum.
Also a compressed spring, we can see that the lighter object with higher kinetic energy.
So you said it again. I'm sorry. Either make a momentum argument or make a kinetic energy argument, but let's not mix the two in this conversation. What's the total compression of the spring? It's a certain amount of pressure, weight. You have to duplicate that weight, that mv coming out. So you're just going to say, look, we have a certain amount of motion and mass that went in, a mass and a velocity. I could put it in one direction, I can put it in two directions, doesn't matter. There's a certain amount of spring compression, and now let's just prove that we're going to get the same amount of motion in the universe out. The same amount of total mass will be moving the same amount of total velocity.
Was able to do more compression work. It was able to compress the longer string in comparison to the heavy object. So this was the point I was trying to make.
Oh, sorry, I don't see the point. I don't get the point. I don't understand the point. I don't see the point.
But yeah, I think that I made here quite strong points.
Okay, well, you can think whatever you want to think. You can think, elephants can fly and all that kind of crap, but I'm not seeing it.
On that momentum alone just isn't enough.
Well, go ahead. Show me the experiment where momentum doesn't work. A momentum explanation doesn't work. Not a subtracting momentum. A momentum argument where you count all the velocity no matter what the direction. All things moving. So you start with stuff moving and you end with stuff moving. Show me the experiment where you don't conserve the momentum.
Explain how springs work. You need something else.
It says you. You said it 6 times now. You need something else. Says you, I say to that. No, you don't. What you need is a piece of evidence. What you need is, in 300 years, you won't admit, well, we really should have videotaped using 4 times the fuel and, to go twice as fast. I mean, we do this twice as fast thing all over the place. We hit the double the speed button all over the place. We press on the gas pedal all over the place. We never videotape the fuel going in. Yeah, you don't have a single experiment demonstrating that bold assertion.
Based on this last experiment here, I would say that kinetic energy makes pretty good sense. Okay.
I mean, fuck. I can't believe you could boldly say that you in any way proved or demonstrated anything about anything making sense or showed any evidence whatsoever. I mean, it's just so obnoxious in a way of you, frankly. To sit there and say that this is somehow you proved or in any way demonstrated that Newton was wrong. Where did you do that? I didn't see it. And Leibniz was right. Where did you show that? Where did you show a bullet doing 2,000 times more work? Damn it. There's just no point in some respects. But anyway, I don't consider this a proper response video to any of my assertions or anything I've drawn. So frankly, I just don't see it. You didn't even clearly make your point, which is somehow you're saying springs don't conserve momentum. Well, show me the experiment where they don't conserve momentum. So I'll show the Professor Lewin clips and a couple of them that are kind of interesting on the subject. And I'll try not to laugh at them, but it's they are what they are. Alright, so here's a Professor Lewin video. So in this experiment, they're doing the things sticking to each other experiments. So we'll play the clip where he's doing the one mass into the one mass, and it becomes the two mass. Momentum is conserved, and kinetic energy is completely annihilated. 1/2 of the kinetic energy disappears. And there's no theoretical sense to it. So we did a bunch of deforming and banging and tragedies everywhere, yet we still have the same momentum, and somehow we did all of these tragic, horrible bendings of stuff without using any momentum. Somehow the train hit the cow and it didn't slow down at all. Didn't lose a tiny bit of its energy. Somehow it moves cows without losing any velocity at all.
This one goes here. This one goes here. Are these two timers on? We don't need this timer anymore. Are they both on? Zero them. Zero them. Are they zero? Okay, you ready? This one is going to plow into this one. They merge and they continue, and then you'll see.
Right. So this is just 5-ton train into, moving 10 miles an hour into 5-ton train moving 0. It becomes a 10-ton train. The momentum is completely conserved, and yet we lose half the kinetic energy, but we have all the momentum still.
The time t prime here. There we go. Ready?
So tacky.
All right.
Crappy commercials on his science videos. I mean, really, he should, the man has some money. He really shouldn't be this desperate. Anyway. I mean, if he's that poor, he should plead and beg for money. What the hell is this crap? Anyway, so clearly, okay, the velocity of the larger object is, a little tiny bit more, it lost a little bit more. It's going a little less than half the speed, a little tiny bit less than half the speed. So it lost a tiny bit of its momentum, and it lost half of its kinetic energy. Completely nonsensical. Used no momentum, yet it did enough work to lose half of its kinetic energy, but didn't lose any momentum. I'm sorry, if you can make sense out of that, I think I can put you in the broken brain category.
What do we?
I mean, that's, 1 plus 1 equals 2. 2 plus 2 equals 4. Come on. 3 plus 3 does not equal 17.
See. 1, 3, 8, 2, 8, 8. 1, 3, 8, 2, 8, 8. 1, 3, 8. 2, 8, 8. Divide this by 2 is 0.144. That is, the difference is only 6, and that is only 4% off. That's completely within my prediction that each time could be off by 2.5%. Now,
so it lost a little tiny bit of its momentum, tiniest little shred of momentum, yet it lost half the kinetic energy. To lose half the kinetic energy, you have to do some sort of work. The explanation is you did work without using any momentum. So I have a bowling ball, I let it hit a pin, the pin flies off, the ball has exactly the same momentum still. It just doesn't make any sense. Come on.
I will have a car which is twice the mass, and this is once the mass. I will set them again to 0.
So he's going to have an error happen here. They're not going to stick to each other, and this will in some way be opposed to, the other experiment where he had them elastically springs bounce off of each other, and 2/3 of the velocity got put into the twice as heavy cart, meaning that it gained 33% more momentum in a direction. Now, I'm saying that experiment is flawed, and I'm just showing you a piece of evidence demonstrating how this is, there's more to this story, because this experiment doesn't illustrate that as a fact. Okay.
And now we get 1 onto double the mass. We ready? There we go.
All right. Ready?
Oh,
Okay, so they bounced. So that's not what he wanted. Clearly, now we're even a lot less. Okay, clearly the speed of the now twice as heavy cart, okay, is a lot more than half the velocity. It's a lot less than half the velocity. Okay, it's not 3 times, but it's somewhere like 2.5 times. It's going slower than half the speed, meaning that it has some energy to keep things going in the other cart. And the fact is, the other cart is still going in the positive direction. So the fact is, it didn't bounce, it kept going forward, which means there's a whole lot of nuance to how these experiments are done, because you would have expected the momentum to be in the opposite direction and retained it in the same direction. So the little cart still has the energy that's missing. You can sort of see that in the experiment. So we'll play it again and look for that.
that each time could be off by 2.5%. Now I will have, it's not a completely inelastic collision. There we go.
So that's when they stick
They made a
together.
slight bounce, which I didn't like.
Okay, so he gets the the 2/3 number this time because of the, but it's a much slower because it's so much more mass. All right, so let's try to get to the right location. I think that's it. No, that's still wrong. The clocks are still wrong. All right, here it is.
There we go.
Watch the little cart.
Oh, you see
Yeah, see, it's going in the same direction still. So it has what the other cart lost in terms of being below complete acceptance. So it should have been 222 if it took all the energy. It obviously can't take all the energy because, frankly, Newton's cradle law says that you can't do this uneven mass thing and get away with it. You can't give things that have not the same mass. You can't directly do the conversion, and even with a spring, you still can't. You need a lever, or some other gears, or hydraulics, or some other system to do those conversions. But clearly, I'm just saying, this number should have been 222, so 50 is still in the little cart, you could argue, of the momentum. But it just demonstrates that there's something unresolved here because there hasn't been enough experiments done to pick out the truth. Toady did the 10-ton train into 5-ton train collision. And again, the argument would be is if you have a 5-ton train with twice the kinetic energy hitting a 10-ton train going half the velocity, that you'd have every expectation, if this has twice the kinetic energy, that it would move the collision in its direction, that it would win the tug of war. And no such thing happens. Both objects hit, and exactly from that location they reflect. The collision does not move in the direction of the object with more kinetic energy, kind of demonstrating that, well, then it must not be real energy. Alright, so that's probably enough. I don't think there's any comments worth my time, but we'll see. It's my memory. Yes. Yeah, I don't think there was any comments. Where'd it go? I'm looking for... it's over this way. Okay, here. Piro. Okay. I like approaching it this way, especially since it's an interesting couple of thought experiments. I didn't even see the experiment in his drawings. I mean, he didn't do any of the experiments. He didn't illustrate what happens in the experiments. I mean, I don't even understand how they were at all illustrative or helpful. he didn't even directly make his assertion that momentum isn't conserved. He just kind of vaguely stated that, I put a 10 mass and a 1 mass, okay, and put a spring between them, that I get equal amounts of momentum in both directions. To me, the fact that energy is related to the change of momentum is enough to show energy is different from momentum. So that doesn't make any sense either. Energy is not related to the change in momentum. Everything that has momentum had to have gotten it from somewhere. I mean, energy has a source. It's a force, of course. Force gives things, material things, energy. Whatever. It's a possession of a quantity of substance. It's a substance. It's something real. But anyway, he will never see it as real. But it would be nice to have a clear thought experiment demonstrating. So it'd be better to have an actual experiment demonstrating. So just show me it taking 4 times the fuel to go twice as fast, and this argument is over. But in 300 years, they can't produce that experiment. Demonstrating this through intuition about springs. Well, again, this intuition word is just about as anti-science as you get. That's the seems like, it seems like a duck, so it must be a duck. Of course, intuition means about 7 billion different things. Now, intuition means you're stupid that you'd even use it in a scientific conversation, because we don't care about what your theory is, whether you got it in 2 seconds of intuition or whether you got it in 500 years of study. The point is what's the credibility of your statement? Intuition doesn't mean anything at all. I mean, intuition is, it looks like a duck. Science is, let's look at it a little further and see what else we see. Because it also looks like a muskrat. Yeah. Intuition shouldn't mean anything to a scientist, and a scientist should be kind of obsessed with what's the best well thought out theory, okay? Not the superficial, simple one. Alright, so I should play the other Lewin clip, yeah, so I'll do that. Because it's just, it just kind of spells it out kind of obviously. Sleepless nights he talks about. It's really at this time here, I think. So I think I should be able to reload it. Oh, it'll probably play another ad. Sorry about that. I can wait it out. I'll try to anyway. Waiting out the ad. Blah, 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 blah. Waiting out the next ad. Blah, 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 blah. Yeah, I mean, again, for this guy to taint his own product this way. Ew. And another ad. I mean, amazing. Just disgusting.
Now, I want you to have a sleepless night. I want you to think about the following. And if you can't solve it before the night is over, then I really think you should lie awake.
So it's absolutely a silly statement where he's saying something has momentum, but it has no mass and velocity and no kinetic energy. So, it's just a silly word game.
Here is the wall. Here is a tennis ball that comes in with a certain mass n, and it has a certain velocity v, whatever that is. It's a nearly elastic collision, and it bounces back from the wall.
Right. So let's just say, well, what if the wall moves when the ball hits? The wall yields. Well, the more the wall yields, the less the tennis ball is bouncing, right? So the lighter I make the wall, the less bounce I get from the ball.
And we all know that if there's a nearly elastic collision, that it comes back with the same velocity. Kinetic energy is conserved. All the kinetic energy is in the tennis ball. Nothing is in the wall. The wall.
All right. So this conserving through bizarre manipulation or something, right? So we know that there's a certain amount of energy, okay, and yes, their claim is it has a certain joules, and the fact is they're going to try to claim that there's this real energy in things, and there's not going to be any place for it to be. There's not going to be any evidence of its existence there.
Has an infinitely large mass. But the momentum of this tennis ball has changed by an amount 2 mv. That momentum must be in the wall. It's
so again, he's making this argument that somehow this is twice the energy. And that would be conservation of direction or something, right? So if I say there's conservation of direction, then I'm obligated to make this change in direction out of energy. But if I say that, no, you don't have to conserve direction, that you can in fact change your direction and it doesn't cost anything. You don't have to buy it with energy. Then that changes the whole theory. Then there's no obligation to think there's 2 mv in the wall. Now, why would I think there's 2 mv in the wall when it's not moving? And even if it's attached to the planet, where do I have any real evidence that the planet ever even knew the wall got hit, let alone that the planet's moving with 2 mv? There's no reason to think so. If it's not moving, then why am I saying it's moving?
negotiable because momentum must be conserved. So now here you...
So again, he says momentum must be conserved. He said it in the other video. So those are two different lectures where he explicitly says momentum must be conserved, and yet all these people are arguing that kinetic energy is conserved and momentum isn't. Does it make any sense to you? No, it doesn't make any sense to me that all these people are doing this arguing from a premise that their own conventional physics teachers don't agree with.
See in front of your eyes a case that the wall has momentum, but it has no kinetic energy. Can you?
So again, there's no evidence it has any momentum. Okay, it's not. I can't measure its velocity. I can't find the velocity component. So I'm looking for the mass and the velocity component that it's supposed to have twice as much of, but I can't find it anywhere.
Understand that? Can you reconcile that? Can you show me mathematically that that is completely kosher? That the wall has momentum 2 mv, non-negotiable.
It is negotiable. It's completely negotiable. There's no evidence that it's actually moving. And there's every evidence that I put it on wheels and I make it move, that I completely change what comes out the other side. So there's every evidence that, yes, I changed the reflection, okay, the reflected energy by absorbing it through actually moving. So if the wall does actually move, the ball doesn't bounce as far. So I'm pretty much pointing out how momentum's conserved, and I don't have to pay any attention to this story that there's 2 mv in the wall, because there's no evidence that there's 2 mv in the wall.
Must have momentum, and yet it has no kinetic energy. How is that possible? Think about it.
So whatever his, so he doesn't give us the answer, because it's some convoluted mush, semantics, baby talk, word gibberish answer, right? That's why he didn't provide it, is because it's going to sound stupid, frankly. All right, so I think that's enough now. Yeah, okay. Done my job and whatnot. So till the next time and such. And so I appreciate the video replies. I will respond to them to a point, I guess. If they're going to keep arguing things with no evidence and just make assertions, I'm probably going to give up at a point. Just say, that's almost... I mean, it's bad enough that the Brozosians are contriving shitty experiments and declaring absolute victory. But you're doing something almost worse, where you're declaring victory without even doing the experiment. I mean, without even contriving the silly experiment to go with it. So if you want to tell me that there's a place that momentum isn't conserved with a spring, then just show me the experiment where the momentum isn't conserved by the spring. And I don't mean momentum in a direction. I mean total energy of the spring, total MV. The spring can produce high V, little m, big M, little v, but it has to conserve the momentum, the force it collected. It has to give back in some way or another, even through its own motion. Alright, so till the next time, and such, and so forth and whatnot.